In my last video, I introduced you to the idea of a Bronsted-Lowry acid. The idea that it's actually a proton donor that takes a proton from one substance and gives it to another substance. But in this video, I wanted to introduce you to the idea of a Bronsted-Lowry base. Because if we have an acid by this Bronsted-Lowry definition, then we also have to have a base. So when we have a Bronsted-Lowry acid, remember it was a proton donor. So when we had our acid, which in this case is hydrochloric acid, HCl, what it is going to do is actually donate its proton. So remember the proton is just an H+. And when it donates that, it gives it to the water. This was what we called an ionization reaction. Remember, that's when a covalent compound reacts to produce ions. So our covalent hydrochloric acid is giving away its proton to the water, producing H3O+, which we called the hydronium ion, and it also produced Cl-. Now, if we have a Bronsted-Lowry acid, that means we also need to have a Bronsted-Lowry base. And a Bronsted-Lowry base is actually the opposite of the acid. It is considered to be a proton acceptor. And so in this reaction, we've talked about how the hydrochloric acid is the acid. It's the thing that's actually donating the proton. But by the Bronsted-Lowry definition, in the same reaction, there also has to be a Bronsted-Lowry base, which in this case is the water. You see, the water is actually taking that proton and accepting it to become H3O+. That is by definition what makes something a Bronsted-Lowry base. So let's take a look at another example of a reaction and identify the Bronsted-Lowry acids and bases in it. Now, in this one, we are going to take NH3, and NH3, just so we can see the molecule, looks like this. And it's going to react with water as well. And water, we already know, has that bent structure with its two lone pairs. And it's going to be in equilibrium with OH minus, which, let's put that up here, so it's in equilibrium with OH minus, which is going to look like this. And it's also going to be in equilibrium with the other substance, which in this case is NH4+. So that's going to be a nitrogen surrounded by hydrogens. And it's going to have a positive charge. Now, what's actually going on here? Well, in this case, this is actually going to be our base. You see, the NH3 is going to accept a proton, but this time it's going to accept it from the water. So the water is actually donating its proton, making it the acid. And since this is accepting the proton, it becomes NH4+. And since water donated the proton, we lose that proton and are left with OH-. This is, by definition, what makes a Bronsted-Lowry acid, and a Bronsted-Lowry base is the idea of donating and accepting protons. I hope there's also something else you noticed, is that in this reaction, water was a base in our first reaction and an acid in our second reaction. And so the Bronsted-Lowry acid and base actually opens the idea to what we call an amphoteric substance. Because Bronsted-Lowry acids and bases are donating and accepting protons, Certain substances can do both. So this is an amphoteric substance, is a substance that acts like an acid or base depending on what it's mixed with. In reality, everything is actually a Bronsted-Lowry acid and base. Most things are technically amphoteric. It really just depends on what you mix it with. And it's more a question of how acidic is it or how basic is it? How willing is it to give up a proton and how willing is it to accept a proton? Because not all substances actually do this equally. The other thing is you may have noticed that I was using reversible arrows to show these reactions taking place. And in my next video, that's what I wanted to address, is the idea that these are actually reversible reactions and can have acids and bases on both sides. So thanks for watching, and I'll address that in my next video. Thanks for watching.